Hello everyone, welcome to this course. My name is Youngjun An and I'm a professor in the School of AI Convergence at Sungshin Women's University in South Korea. In this lecture series, I'd like to introduce our recent research on shape motion prediction using artificial intelligence and modern deep learning techniques. Before we begin, I would like to acknowledge the organizations that made this research possible. This work was financially supported by the Lloyd Register Foundation, which supports research aimed at improving engineering safety around the world. Our research was conducted as part of a collaborative project led by Seoul National University, and our research group at Sungshin Women's University participated as a joint research institution. I'd like to express my sincere appreciation to the research team at Seoul National University for their continuous collaboration and support throughout this project. In this repository, we've organized not only the source code, but also the datasets, trained models, and analysis notebooks so that anyone can reproduce our experiments. So let's start by taking a quick look at the README file and see how this repository is organized. Before we dive into the code, let's take a quick look at the GitHub repository. This repository contains all of the materials used throughout this course, including datasets and trained models and example notebooks. So here is the notebook. So if you clone this repository, you'll be able to reproduce every experiment that we'll discuss. First, we establish the theoretical background by analyzing shape motion data generated from numerical simulations and model scale experiments. Second, we develop and compare several deep learning models for shape motion prediction. Throughout this notebook, you will see architectures such as time CNN, TCN, modern TCN, and several hybrid models. The third topic is uncertainty quantification. Besides making predictions, we also want to model to estimate how confident it is about those predictions, which is very important for safety critical applications. And finally, we investigate data sufficiency. In other words, how much training data do we actually need before the participation performance starts to saturate? Later in this notebook, we will perform several experiments to answer that question. So now let's briefly look at the repository structure. The main notebook is comparison models, IPY and BIP file. This is where almost all of today's experiments are implemented, and you will probably spend most of your time working inside this notebook. And the dataset folder here contains the regression datasets. Each CSV file represents one simulation condition with different wave heading, wave periods, significant wave heights, and ship speeds. Wave heading angles and periods, and significant wave heights, and the vessel speed. There are the dataset will be used for continuous shape motion prediction. And the dataset grid folder, this is much simpler datasets, and is generated on a structured parameter grid. We'll mainly use this dataset when comparing different neural network architectures under controlled environmental conditions. So that's the overall structure of the repository. Everything we'll do in this lecture, from loading the data, training models, comparing architectures, and visualizing prediction, is organized inside these folders. Now that we know where everything is located, let's start exploring the datasets themselves. Okay, so the first thing is the comparison of models, IPY and B file. And it shows a brief introduction, the shape motion prediction techniques using the AI models. So, all right, let's start with the big picture here. Before we jump into the data sets, the neural networks, or any of the code, I want to spend a few minutes talking about what we actually mean by shape motion prediction. At first, this might sound like one single problem. We have a shape, it moves, and we want an AI model to predict where it is going next. Pretty straightforward, right? But here's the catch. Shape motion prediction can mean very different things depending on how far into the future we want to predict and what kind of shape behavior we are interested in. So predicting what a ship will do 5 seconds from now is a very different problem from predicting its fuel consumption over the next 2 or 3 months. And both of those are different from predicting how a ship will turn when the rudder is applied. So in this table here, I dived the problem into 4 broad categories: short-term prediction, mid-term prediction, long-term prediction, and maneuvering prediction. These categories are not perfectly separated in real application. Of course, there can be some overlap. Still, this classification gives us a useful roadmap for understanding the research problems and for selecting an appropriate AI models. Let's first look at the role called prediction horizon. The prediction horizon simply means how far ahead the model is trying to predict. Here. For short-term prediction, we are usually talking about a few seconds to several tens of seconds. Imagine that a ship is moving up and down in waves, and we want to know what the deck position will be 10 seconds from now. Now, that would be a typical short-term prediction problem. Mid-term prediction usually covers several tens of seconds to several minutes. At this time scale, the model has to consider more than just the ship's current moment. The surrounding waves, wind, and current can have a major influence. Long-term prediction can cover anything from several tens of minutes to several days. At that point, we are no longer focusing on every small roll or pitch motion of the vessel. Instead, we are usually looking at higher level operational behavior, such as where the ship will travel, when it will arrive, or how much fuel it will consume. The last category is maneuvering prediction. Its time horizon may also range from several tens of seconds to several minutes. So it may look similar to medium-term prediction. However, the underlying problem is different because the primary cause of motion is often a control input, such as the rudder angle or propeller operation. So one thing to keep in mind is that the prediction horizon also does not completely define the problem. We also need to ask what is physically driving the ship's motion. Now let's move to the primary objective, the role. The main goal of the short-term prediction is the immediate prediction and control of ship motion. A good example is helicopter landing assistant on the ship. When a helicopter approaches a moving deck, even a small error in the predicted deck position can matter. The system may need to estimate the ship's heave, roll, and pitch several seconds into the future so that the pilot or an automated loading system can determine a safer loading moment. Another possible application is the acceleration of an electric propulsion vessel. When an electric ship suddenly starts or changes thrust, the control system may need to predict the vessel's immediate dynamic response. So short-term prediction can also support motion stabilization and active control systems. In other words, short-term prediction is closely connected to real-time decisions. The prediction has to be produced quickly, and it has to describe the near-future motion in detail. So next, medium-term prediction. The goal is broader. We want to predict the future behavior of the ship overall over a longer interval, often while accounting for environmental forces. For example, we may want to know how the ship will roll, pitch, or heave over the next 1 or 2 minutes under a given wave condition. This information could support operational decision-making, motion control, or safety assessment. Long-term prediction focuses more on voyage planning and operational efficiency. We may want to estimate the ship's arrival time, fuel consumption, or optimal route. The goal is not to reproduce every oscillation of the ship. Instead, the model should capture larger operational trends. The last one is the maneuvering prediction. The objective is to estimate maneuvering performance or the future trajectory of the ship. For example, given a particular rudder command and propeller speed, we may want to predict how quickly the ship will turn, how large the turning radius will be, or what trajectory it will follow. Now, let's compare the input information used in these four categories. In short-term prediction, the main input is usually the recent ship motion time series. For example, we may provide the model with the last 30 seconds of surge, sway, heave, roll, pitch, and yaw, then ask it to predict the next 10 seconds. Why can this work without explicitly giving the wave information? The reason is inertia. The large ship cannot instantly change its motion. Its current state contains a lot of information about what will happen in the very near future. If the ship is already rolling to one side with a certain angular velocity, it is likely to continue that movement for at least a short period of time. It is similar to watching a ball that is already moving even without knowing every force acting on the ball. You can make a decent guess about where it will be a moment later based on its current position and velocity. Of course, this does not mean that waves are irrelevant. The waves are the original cause of much of the motion. However, over a very short prediction horizon, their effects may already be embedded in the observed ship motion history. That is why short-term prediction models can often rely primarily on historical motion data. For medium-term prediction, this becomes more difficult. As the forecasting horizon grows, the model cannot rely only on the ship's current inertia. New wave events will affect the vessel, and their influence becomes increasingly important. Therefore, medium-term models often require both ship motion measurements and information about external forces, such as waves, wind, and ocean current. This raises an important research question: how should we provide wave information to an AI model? Should we use measured wave elevation? Should we use significant wave height and wave periods? Should we use radar-based wave predictions? Or should the model infer the wave condition from the ship's previous motion? There is no single answer, and this remains a major area of research. Earlier studies often relied heavily on simulated wave and ship motion data because simulation allows us to control the environmental conditions precisely. More recently, however, the problem has started to move toward full-scale on-board measurements. In other words, researchers are increasingly asking whether these models can work using actual sensors installed on operating ships. This shift is important because real-world data are much messier than simulated data. Sensors contain noise, measurement may be missing, environmental conditions may not be fully known, and the vessel may operate under conditions that were not represented in the training data. So, moving from simulation to full-scale measurement is not just a matter of collecting more data, it changes the nature of the AI problem. For long-term prediction, the input information is different again. Instead of using high-frequency 6DOF motion data, long-term models often use AIS data, weather information, voyage records, and operational variables. AIS stands for Automatic Identification System. It provides information such as the ship's position, speed, heading, and timestamp. When AIS data are collected over a long period, they can be used to learn common shipping routes and operational patterns. For fuel consumption estimation, the model may also use ship speed, drafts, engine power, weather conditions, and sea state. For route optimization, the inputs may include the departure point, destination, forecast weather, current wave conditions, and operational constraints. So the input data become broader and broader, heterogeneous. The model is no longer learning only one model signal. It has to combine several types of operational and environmental information. In maneuvering prediction. The important input include the rudder angle, propeller operation, and ship motion measurements. The rudder and propeller are especially important because they act as the main control inputs. We want to predict the ship's turning behavior. We need to know what command was given to the ship. Without the rudder input, the same current motion state could lead to very different future trajectories. Now let's move to the role called external disturbances. For short-term prediction, explicit external force information is generally less critical. For medium-term prediction, external disturbances are essential. The longer the prediction horizon becomes, the more the model needs to know about future wave excitation. If the next large wave has not yet affected the ship, it cannot be inferred perfectly from the current ship motion alone. This is one of the fundamental limits of pure autoregressive predictions. If we only use the past ship motion, the model can predict the continuation of the current pattern, but it cannot know about completely new environment events that are not represented in the past sequence. For long-term predictions, environmental and operational information is also important, but it is used at a different scale. Instead of predicting every individual wave response, the model may use average weather conditions, forecast states, or route-level environmental information. In maneuvering problems, the primary external excitation is usually the control input itself. The rudder angle and propeller thrust drive the maneuvering motion. Now let's look at the dominant physical characteristics. Short-term ship motion is often dominated by inertia, of course, and mid-term motion is more strongly influenced by linear dynamics and wave-ship interactions. And long-term prediction is dominated more by operational patterns and environmental changes, like a ship may slow down in rough weather, follow a particular traffic route, wait near a port, or change speed to meet a scheduled arrival time. These are not simply mechanical oscillations. They reflect operational decisions and repeated human or organizational behavior. Maneuvering dynamics are often slowly varying. Turning circle starts like this and goes like this. This creates an interestingly challenge for artificial intelligence. In maneuvering tasks, the control inputs do not change very frequently. For example, in a standard turning circle test, the rudder may be moved to a fixed angle and then held there. The resulting ship response changes gradually. From a neural network's point of view, this maneuvering control, this type of data may not provide very diverse temporal patterns. Many parts of the time series can look similar, and the model may have difficulty learning a broad range of maneuvering behavior. That is why random maneuvering has become an important research topic. Instead of using only standard maneuvers, we can apply randomly varying rudder commands or propeller inputs. This generates richer dynamic responses and covers a wider range of the state space. You can think of it like this. If you want to teach a model how a car behaves, it is not enough to drive only in a straight line and make one left turn. And you need a variety of acceleration, turns, stops, and combination of controls. Random maneuvering serves a similar purpose for ship dynamics models. So now let's move to the representative research topics. For short-term prediction, the central topic is simply motion prediction. We are trying to estimate the immediate future motion of the vessels. And the wave prediction may mean predicting the future wave elevation near the vessel or reconstructing wave information from the measured ship motions. Parametric roll is a particularly important safety issue because it can produce large roll motions under certain wave conditions. An AI model that can recognize or predict the onset of parametric roll could provide an early warning. For long-term prediction, the major topics include ETA prediction, fuel consumptions, estimation, and route optimization. ETA means estimated time of arrival. Even though it sounds simple, accurate ETA prediction can be difficult because ships are affected by weather, traffic, port conditions, and operational decisions. Fuel consumption estimation is closely related to both environmental impact and operating cost. Route optimization combines these predictions. The model may search for a route that minimizes fuel consumption while satisfying arrival time and safety constraints. For maneuvering research, major topic includes maneuvering prediction and motion coefficient estimation. Motion coefficient describe how forces and moments change with the ship's motion and control inputs. Traditionally, these coefficients are estimated using experiments, computational fluid dynamics, or system identification methods. AI model can provide an alternative way to estimate these coefficients from time series data or to predict maneuvering response directly. The final one is the short-term AI research characteristics. For short-term prediction, the main focus is time series pattern learning. Models such as recurrent neural network and temporal convolutional networks are natural choices because they are designed to learn temporal dependencies. RNN-based models include the standard RNN, LSTM, and GRU. These models process a sequence step by step and maintain an internal hidden state. TCM-based models use one-dimensional convolution along the time axis. They can process many time points in parallel and often train faster than recurrent models. Later in this notebook, we will look at several convolutional-based approaches, including time CNN and modern TCN. For medium-term prediction, physics-aware AI and multimodal learning become increasingly important. Physics-aware AI means that we do not treat the problem as a completely generic sequence prediction task. We try to include physical knowledge, constraints, or variables related to wave-shape interaction. Multimodal learning means that the model combines different types of information. For example, it may use motion sensors, wave measurements, weather data, and radar information at the same time. For long-term prediction, large-scale sequence modeling becomes important because AIS and Voyage datasets may contain millions of observations collected across long periods. Model needs to capture long-term patterns, interactions among vessels, environmental trends, and operational behavior. For maneuvering prediction, hybrid physics plus AI approaches are essentially promising. Purely data-driven models may have difficulty because maneuvering datasets are often limited and do not cover every possible control conditions. By combining physical equations with machine learning, we can reduce the amount of data required and improve physical consistency. So let's step back for a second. The key takeaway from this table is that there is no single best AI model for every ship prediction problem. The right model depends on the prediction horizon, the available inputs, and the dominant physics. For a prediction only a few seconds ahead, using motion history and fast TCN may be enough. For a prediction 1 or 2 minutes ahead, the model may need explicit wave information and a better representation of wave-shape interactions. For a prediction over hours or days, a month, AIS and operational data become more relevant than high-frequency motion data. And for maneuvering prediction, control inputs and physical modeling are essential. This is the framework I want you to keep in mind as we go through the rest of this notebook. In the next section, we will focus mainly on short-term and medium-term motion prediction. We will look at how the datasets are organized, how different neural networks architectures process the time series, and how the prediction results change as we modify the model structure and the forecasting horizon.